everyone, this is the lesson on double displacement. Specifically, we are looking at neutralization reactions and acid-base nomenclature. Okay, so taking a look from last year, we had seen this image before where we have an acid plus a base reacting together to form a water and a salt. Another name for salt is an ionic compound. All right, so if you ever see the word salt, know that it's just an ionic compound. Okay, how do we get the water? Well, your acid will start with a hydrogen, okay, and your base will either end in a hydroxide or a carbonate. Okay, and that's how we form our water. If we have a carbonate as our base, we will also have carbon dioxide gas produced. Okay, so remember that a neutralization reaction is a reaction that is a type of double displacement. Okay, it's not its own category, it is a type of double displacement. Specifically, it is where an acid and a base will react to form a water and an ionic compound, okay? Because the goal that when our acids and base react, they will neutralize each other. So you'll see that we're aiming to achieve our solution of our product to be a pH of around 7. So here's an example. If I have nitric acid reacting with sodium hydroxide solution, okay, and I'm going to remember when I'm writing this out that every acid and every base has to be aqueous, okay? So when I write out this equation, okay, what you're going to see is that the hydrogen and the hydroxide are going to form your H2O. That's liquid, that's water. Okay, water is always liquid unless it's subject to heat when it becomes water vapor. Okay, and then our salt comes from the metal and the polyatomic anion. So you get NaNO3. You can use your solubility chart to figure out the state. Nitrates are always soluble with everything, so it would be NaNO3. Check that it's balanced. It is balanced, and proceed to the next question. Okay, so during a neutralization reaction, the solution produced will have a pH closer to 7 than its reactants, right? We know pH 7 is neutral. Note that these reactions generally do not form precipitates. So unlike the previous lesson where we learned about precipitate formation and gas formation, neutralization does not form precipitates, and all three of those categories are double displacement reactions. Okay, they're just like subcategories. You can detect that a reaction has occurred by testing the pH of the final solution. So we could do that in a laboratory setting. Now, there are two specific cases for neutralization. You can have neutralization with a base that is a hydroxide compound, okay, where you will just produce a water and a salt. Or you can have a neutralization reaction where the base is a carbonate compound, okay? And in this case, you're also going to produce carbon dioxide, water, and a salt. Okay, you learned this last year, so this is just some review. Remember that you're looking for a base to have some kind of metal with a hydroxide, okay, and it's going to have to be aqueous state, or it's going to be some kind of metal or a positive polyatomic ion with a carbonate. Carbonate has a charge of 2 minus. Okay, and it will be aqueous. So those are your two options for bases. Look out for those to identify neutralization reaction. So when we're talking about nomenclature of acids and bases, naming bases is pretty straightforward. You use the same steps as your nomenclature for simple ionic compounds with polyatomics. So I look at my periodic table and I see that Mg is magnesium. I look at my polyatomic table, OH is hydroxide, and I have named my base. Now, if I was doing the opposite, I have to remember to always write aqueous beside acids and bases when I'm writing the formula. Okay, now let's take a look at LiOH. If I look at my periodic table, Li is lithium. And OH is hydroxide. And I'll do one more. Let's say I have sodium carbonate as an example, Na2CO3. So I would name that sodium because that is my metal, and carbonate, because that is my polyatomic. Remember, you have to know your eights, your hydroxide, your ammonium, and your cyanide for your test. So make sure you're memorizing those. Then NaOH is sodium hydroxide. Again, your naming, follow your ionic compound steps. With polyatomics sometimes, okay? Now, what is new to us this year is naming acids, okay? You can usually tell that a compound is an acid if the chemical formula starts with one or more hydrogen atom, okay? Water is an exception. So we use two different systems to name acids depending on whether or not the compound will contain oxygen. The first one that we're going to look at is what do we do when we have an acid without oxygen? And then we're going to take a look at what do we do and how do we name an acid with oxygen. So an acid with oxygen is when you have your polyatomics present. So when you have an acid without oxygen, so kind of this formula, generic formula, you're going to make sure to use the prefix hydro and you're going to end it in ic acid, okay? And the stem or the base of the acid comes from the name of the element, okay? Following the hydrogen in the formula. So look over here, HF, F is fluorine. It does not have any oxygen in this formula, so it's just hydrofluoric acid. The next one is HCl, okay? Cl is chlorine, so it's hydrochloric acid. HBr, Br is bromine, so it's hydrobromic acid, okay? Again, no oxygen present. You have to have the hydro prefix before and the ic acid after the stem of the word, okay? Again, notice you have to always write your aqueous state for acids and bases. Never ever forget that, because if I didn't have that aqueous, it would just be called hydrogen fluoride. Okay, as soon as I add that aqueous state, it is now hydrofluoric acid. Now, the second step for naming acids is recognize if I have an acid with oxygen. So here's where you're looking, do I have any polyatomic ions present? Okay, so it's going to be X and plus some sort of polyatomic. Because most polyatomic, most polyatomic ions will contain a oxygen, okay? These acids are called oxyacids, and their names are based on their anions, or oxyanion, which are negatively charged polyatomic ions that contain oxygen. So note that the names of these acids do not start with hydro. Okay, so as soon as you recognize oxygen, you will not use that prefix. Instead, what you're going to do, if it ends in ate, your ending is ic, and if it ends in ite, your ending is us. Okay, so here's an example. If I have, and here's your generic formula to remember, if I have a hydrogen plus just a carbonate and I don't see that aqueous state, it's just going to be hydrogen carbonate, the way you would name any compound. The next example is H2CO3 aqueous. Now notice there's that aqueous that tells you it's an acid. So it's actually, as soon as you see aqueous beside it and you have to write it too, that is carbonic acid, okay? Now, if the oxyanion name ends in ite, the acid name ends in us. So, for example, again, here's your generic formula. If I have H2SO3, SO3 is sulfite, okay? Whereas SO4 is sulfate, okay? So if it's sulfite, H2SO3 is hydrogen sulfite. Now, if I have H2SO3 and I put aqueous beside it, that is now sulfuric acid, okay? And it doesn't matter if you write sulfur with an F or PH, both are correct, okay? So, couple of notes. Ate means there's more oxygen in the anion than the one ending in ite. For example, sulfate has one more oxygen than sulfite. Nitrate, NO3, has one more oxygen than an anion of nitrite. Now, if you look at your table for polyatomic ions, okay, the easiest way to recognize when you have one more or one less oxygen is just to look at the pattern, okay? Your eights are kind of your bases. That's how many oxygens should be present. So let's look at chlorate. Chlorate is ClO3. As soon as I have minus one oxygen, okay, my ending is ite. So I would do us acid, okay? If I have minus two oxygens from our base, which is 8, okay, we have the prefix hypoite, okay, hypochlorite. So I'm going to name it hypochlorous acid. And then let's say I have one more oxygen. Then I have perchlorate. So we would call it perchloric acid, where you have the ic acid, but then you have the prefix per. Okay, so the main ones we're going to focus on are the 8, which become ic acid, so chloric acid, whereas we'll also see often ite, and sometimes in your practice you'll see hypochlorite or perchlorate, but most frequently you see the ate or ite ending, right? If I look at nitrate, nitrate is NO3 minus, nitrite is NO2 minus. The charge does not change, it's just one less oxygen. Okay, so as you are working away on your practice, okay, first practice nomenclature of acids and bases. Check your answers. So for example, HNO3, what is my anion, right? My polyatomic, I call this nitrate. Name of my acid, because it has oxygen, is going to be nitric acid. Now let's compare that to, let's say I had H3N, aqueous, right? It's just nitrogen. So I would have to call that hydronitric acid. Again, that doesn't exist, but that would be the name because it would not have an oxygen, okay? A better example of this would be if we take a look at something with chlorine. So HClO3 is your anion, which is chlorate. So we call this chloric acid. Now let's say I had something just HCl, aqueous. I would see that I have chlorine as my anion, which means it would be hydrochloric acid because it does not have any oxygen present. Okay, so please try this practice and go through the answer key and then practice your neutralization reactions. Remember, now you have to write your states. Thanks so much. See you in class tomorrow.